All right, everybody, welcome back. Episode 14, lesson 14 of Uncertainty and Probability Theory, the Logic of Science. Today's content, 1, 2, 3, many. We're going to learn to count and why that's important. But before we get to that, I want to discuss the series itself. I had some comments, particularly by Hagfish, and some real life happenings about the level of difficulty of this class and how we might attack some of this. I originally today, and I recorded the David Stove's proof of using the symmetry of logical constants to prove the statistical syllogism, which we'll talk about in just a second. And I did all that, and then I had very little time left to even discuss counting, and I rushed through it. I thought, boy, this is horrible. If I release this stuff, people are going to think I'm some sort of lunatic. I don't know. I mean, I was just driveling on about counting and not explaining things at all. And meanwhile, I was going into depth of this proof, which I think is very lovely and important. But there's maybe 10 guys in the entire world who would be interested in this. And 9 of those 10 guys don't even know they're interested in it. I mean, probability is thought to be set and fixed into this frequentist or a meld of that and this idea that it's completely subjective, both of which are false statements. So not everybody even knows they need this. So I decided on this tack. I think what we'll do is keep the lectures somewhat simple. And for difficult proofs, like I did last week for Percy Diaconis' attempted proof of the statistical syllogism in finite information, is to leave that stuff for the comments. And if people have questions, they're welcome to. I'll leave it to the written lecture. And if people have comments and so forth, they can leave them, or they can email me or contact me in any other way, and I could go over those difficult proofs themselves. But for these lectures, I'm going to stick to somewhat more of a surface level to show you why I think all of it is important. That's the key, and I don't want to miss that. And I think I was missing that, and I want to amend that error while I still have a chance. So, let's see what we've learned. We have learned so far quite a lot of philosophy, but we've also learned that probability can be a number. And we know it takes a certain mathematical form, which turned out to be Bayes' theorem. And we know so far, anyway, it could take two numbers. We have proved it could take two numbers. 0 for locally false, and 1 for locally or conditionally true. Those we did. And then we also introduced a statistical syllogism, again, we discussed just a second here, in which we learned we could assign other numerical values between 0 and 1 to these probabilities. And I did promise you the proof of why the statistical syllogism itself works. Because we need to understand, if probability is going to be a measure of our uncertainty, how do we know that any numbers can be used for it at all? Well, that's what we've done. And that's what Stove's proof is going to do. And I'm going to leave that to the written lecture, which you can find on my website or Substack, which will be listed in the comments below the video comments, or if you already know how to find it. So it can be proved. The statistical syllogism can be proved. And that's how we got to this. Let's remember our homework question. We have evidence that we had a Metalunan interocitor that can take and must take. It can take and must take one of 6 states. S1, 2, 3, up to 6. Given only that information, we surmise the probability it would be in state 6 is 1 over 6. Because each of these states we have no more information about than the other, so there's no reason to think any one is more likely than the other. Now that can be proved, as I say. Jaynes tried it and Diaconis tried it, and I think they failed. They had circular proofs. Stove does not, and that'll be in the comments. So, but it's a technicality, if you like, but it's very important, I think, for those who really want to get in depth to understand what probability really truly is. And we're going to get into more of that, the consequences of that later. Now, this is no different. We can consider this a Metalunan interocitor. We don't have to, but if we do, this becomes a model of this. This is our uncertainty in the model of this. This does not state anything about the reality of this, except that it does indeed have 6 states, and they're nicely labeled for us, 1, 2, and so forth. And when we throw it, it must come and realize one of these states. All right, so it's a model of what we're going to see. And to prove that to us, we added this information fair. Now, what could possibly fair be? Fair means, if it means anything, it means symmetric. So we were arguing with the word fair there that we're going to assume that this dice, or die, or any number of dice, is perfectly symmetric, which we know is false. This one here has got 6 dots drilled out of it on one side, 3, and then 1, and so on. So the symmetry's out. It has little bits of lumps, and I'm sure if we were to examine this under a microscope, we would find any numbers of departures from symmetry. And then not only that, we had to consider how we were going to toss it, and what condition does it leave my hand with, how much spin and force, and on what type of surface is it going to bounce around, and all these kinds of things. There is no such thing as fair. All right, there's no such thing as fair. There are such things as causes. So we must separate. This is there's 2 lessons in this entire class. And if you only come away with these 2 lessons, you're going to understand 95% of science. And those 2 lessons are, this is uncertainty. This is the epistemology of the situation. The actual physical reality is the ontology. The epistemology gives our uncertainty of the ontology. But the 2 are not equivalent. To make that mistake is to commit the deadly sin, which I always say, the deadly sin of reification, or reification, however you want to pronounce it. This is to assume the model is reality. The map becomes the territory. This mistake is exceedingly common if you don't keep in mind what the limitations of probability are. It plagues quantum mechanics, for instance, but not just that. It absolutely does a number on any kind of, and the so-called soft sciences that make use of statistics and probability models. So this, if we learned, if it does anything to the ontology, defines the probability as 1/6. That's the 3 things in the equal sign, a definition. It becomes a circular argument. This states the probability of S6 is 1/6, and so the probability of S6, given the probability of S6 is 1/6, had better be 1/6. So we've done ourselves a circular argument here. And for those people who did not understand that, I asked them to add the words unfair. Take out fair, and we'll put in unfair. Now, what could that mean? Aha. Here's the second lesson. The second most important lesson, in fact, I think it's the most important lesson in all of this class. If we change the information on this side of the probability schema, this is all of the evidence. Somebody was asking me, where do you get your evidence? Well, it's us, it's we who supply the evidence. We always assume this evidence is true. Absolutely, every time we assume this evidence is true. Doesn't matter if we have other information that says it's false. That's irrelevant to logic. And that's what probability is. It's not a branch of logic, it's part of logic. It's the completion of logic. We assume this evidence is true, and we want to know about this. We assert this proposition. We want to say, what does our evidence say with respect to this? And it's this little connecting rod right there, if you like. That little connecting rod is what all of logic is. All of logic is only describing that rod. It says if we assume this evidence is true, here is what the uncertainty in this is. That's it. If we change the evidence, we change the probability. Anything on this side, if we change the evidence on this side, we change the probability, unless that information is irrelevant. And an example of an irrelevancy, which would be used in Stove's proof, which would be to and this by some necessary truth. You could read about that. But obviously, if I just put something that's necessarily true here, whatever that necessary truth is, 1 + 1 = 2, for instance, that's not going to change this probability. So as long as the evidence we put on this side is changed and is probative to this question, the probability changes. It says nothing about causality. We learned more about that today. Now, unfair. What does unfair mean? Doesn't mean anything. That's the problem. Now we have to have tacit definitions. All of us will come to this word unfair and put in different information in here now. We're going to be assuming different evidence. Some people think unfair. Well, that Briggs is a tricky guy, and he already said he does amateur magic. So maybe he's weighted it so that the 6 will always show top. That's a piece of information that you would assume, and that would change the probability. If that's the case, and it's 6 weighted, then you would say the probability is 1. That's supposed to be a weight, WGT or something, whatever. All right, if you say, well, this guy, I know Briggs, and I know he does this amateur magic stuff, and I know he'd probably want to weight it to 6 to fool the audience, but I know he would want to weight it to the 6, and then he would know the audience is thinking of that, so what he really did was weighted it to the 1. Therefore, I'll just call that the complement of the weight thing. The probability is 0 if you assume that tacit information. Or you could say, I don't know what's going to happen. I don't know. We do know that part of this evidence is still true. It has to be S1, 2, 3, 4, 5, 6. So the probability of S1 plus the probability of S2 all the way 6 still must equal 1. That's true. So something has to happen in there. That probability has to be distributed among these sides one way or the other. Maybe the best we could say is that this only tells us that it's contingent. And it's 0 to 1. It's just somewhere in the 0, 1 we have an interval. And we don't know how to assign it. Or we could think of it this way. What if I asked you to make a bet? You have to pick. I'm the instructor. I'm going to make you write down on a piece of paper which of these states that you think is going to come up, that you think is going to eventuate or obtain, or however you want to put it. S1 through 6, which one would you put? And what would your reasoning be? With that side of reasoning, you might say, again, I don't know the difference. He could have weighted any side. And if he could have weighted any side or shaved any side or done something to the unfairness of the toss in any way, I don't know what that could be. So again, the probability is 1/6. So there is no answer to this question. It depends on the tacit information you bring to this. You change that information, you change the probability. None of it changes the ontology. Okay. That illustration, I think, is excellent because you have to spend time pondering this. You have to get out of your mind that probability is telling you something physical about objects. It is not. You assume that stuff in the evidence. It's you who bring those assumptions. All probability is of the schema y given x, which is a very common way to write probability models in statistics. It's you who brings that information there. You who brought the ideas of cause or the physics of the situation or the material constituents of the experiment that you're doing and all that kind of thing. It's you who brought that there. You. It's the assumptions that you bring, and then you calculate the probability of something of interest with respect to that. All probability fits this scheme. You change this evidence, you change the probability. You change the evidence, you change the probability. That's it. Okay. Now, counting. Counting is... I'm halfway rambling through this lecture here, and I'm not going to be able to teach you all of combinatorics. That's the science or mathematics of counting, combinatorics. How do we combine things? And the reason that's interesting is for all kinds of things, because probability can be directly related to how we assume a certain set of objects is going to obtain. So we'll go through some examples of that. But I can't teach you all of combinatorics in the next 10 minutes. It is an impossibility. I'm going to list some links and so forth on the blog and in the notes below and things like this. But I can't do it. The best I'm going to be able to do is teach you a couple of things, and then we'll bring in other bits of combinatorics when we need them. I'm not going to teach you calculus either, and we're going to need that. So we'll just have to assume something. But it's good to have a few of these formula under the belt. So I like to teach this famous song by George Thorogood, one bourbon, one scotch, and one beer. I already got a B, so I'll use an R for the beer. And he wants to do a tasting. The tasting is all the rage, all these wineries and distilleries and the like. And so this distillery might make all of these kind of things. And so the barmaid has to pour them out. How many different ways can she pour these drinks? And the order makes a difference because the taste of bourbon, if you don't get it completely out of your mouth, can affect the taste of scotch that you might have second, or beer that you might have third, and so forth. So the order makes a difference. Well, if we're going to set the glasses up, we have three choices for the first one, either bourbon or scotch or beer. And after we pulled one of them away, we have two choices for the second one. And by the time we're done, we only have one choice for the third, which equals 6. There's 6 different ways. If you like, you can enumerate them. There's bourbon, scotch, beer. There's bourbon, beer, scotch. There's scotch, bourbon, beer, and so forth. This numbers of ways of arranging, where the order matters, has a formula, and it's n factorial is the way we write this. So this is 3, it'd be 3 factorial, and it's just exactly what it says. This is n times n minus 1 times n minus 2 times 1. This came from the calculus of gamma functions, and so without having to teach that, it happens to be the case that if you put this is just notation. It's just notation. So we put 0 into this gamma function. It turns out 0 factorial equals 1. And I'm not going to teach that. You can learn about gamma functions on your own. This is just a shorthand way of writing this notation, so don't get yourself caught up on this. All right, so we need that, and we have other things. So, for instance, it's real simple. If I have four philosophy books, and I got, I don't know, 3 math books, and I got 2 of my own books, Briggs books, and I'm a librarian, and I have whatever the Library of Congress system is or whatever. I don't have access to this. How many different ways can you put these on the shelf? Such that the philosophy books stay together, the math books stay together, and my books stay together. So you want to have the philosophy section separate from the math section from the Briggs section. Well, there's 4 factorial ways to do this. There's 4 ways of arranging them, and then we got 3 ways to arrange this. So that's 3 factorial. This is 2 factorial, and so these set could come second or third. This set could come first or third. This set could come first, second, or third. So we multiply these together. That's it. That's the answer how to arrange. So we can apply that arranging formula more generally. Okay, I've given you the absolute lightning tour of how to count. And I'm just showing you how it can get involved very quickly. This is very simple stuff right here, but it can get bizarre. It can get bizarre. So, for instance, I'll leave this as part of the homework. Airports around the world, at least those that are international and so forth, have 3 letters, a 3-letter designation. How many different airports can there be? So I'll write that for people who can't see it. How many different airports can there be? They have a 3-letter designation. You tell me. That's one thing you can do by learning to count. Now, suppose I have 10 people in a class. I got 10 people watching this live or something like this. And I want to form groups of 2 of them to pair them off to do some homework where each one quizzes each other. So I got 10 people and I want to form groups of 2. How many different groups of 2 can I have? Well, I can form a group of the first person and the second person. But that's a group. It doesn't matter if I pick the second person first and the first person second, or the first person first and the second person second. Doesn't make any difference. So this is the number of ways of arranging things where the order doesn't matter. So in that library book example where I don't care about the orders of the book, if they're all exactly the same, 4 philosophy books, same 3 math books, same 3 Briggs books, The way I can order now, I have a set of 3 different kinds of books, and suppose they're all the philosophy books are the same, all the math books are the same, and all the Briggs books are the same. Now, how many ways can you arrange them? The order inside each category is now irrelevant. I've got 3 of them, and I have to arrange just those 3. You tell me the answer. Or in a class I have 10 people, I want to take off groups of 2 of them. And I'm just going to show you the formula because I don't have time to do anything else. It would be, we write it like this. I have 10 people and I'm going to choose 2. And in general, I'm going to have n and I'm going to choose k. And that's going to equal n factorial divided by n minus k factorial. You're just going to have to trust me on this right here. It's just a little bit of math that we need. And there'll be, I have proof in my, this book is linked on the site free. I have proof of all this kind of thing here. My number 2 son did the art on that. All the basics of counting are in that book. Absolutely free. You don't have to pay for any of this stuff, so don't worry about that. That's that formula. There's also permutations where I have a group of n things, and I only want to take 5 of those things, for instance. I'm going to take only 5 out of the n. I'm going to take 5 out of n, and I want to arrange those 5. That formula happens to be similar to this, where the order doesn't make any difference out of just those. I mean, the order makes a difference in these, and that's n factorial divided by n minus k factorial. Permutations. I know I'm blazing through this because I want to get to the point where we use all this formula, and if you don't understand it, I get it. I'm going to give enough hints in the written lecture and everything that you're going to be able to figure this stuff out in the homework I'm going to give you. Meanwhile, I want to start back. I left my notes off camera there. I want to start back in chapter 3 in Jaynes. We'll do a little bit from there to prove a very important point, and then we'll move back into chapter 3 or 4 of his, and then back to mine, and back and forth and so forth. So I have information. This is Jaynes notation. I have information in which, let me get the exact number right here. There's an urn with n balls. For whatever reason, he has m of them are red, and that must mean, and then he has n minus m are white. And he goes on, what I think makes another mistake. It's not a big mistake. The math is immaculate as always. He goes on and talks about, well, the balls are all mixed up, and I have a blindfold on, and I can't see what I'm drawing. None of that is relevant. That's just like saying there's a fair coin. There is no such thing as a fair coin. There's no such thing as a fair urn. You can't have a fair urn. You don't know what's in there. You don't know the order the balls are in there, how people are going to draw them. None of that stuff is relevant. And in fact, this could just be yet another interocitor. So, what have we learned in probability? Well, we've learned that the probability of A and B given C equals the probability of A given BC times the probability of B given C. And this is equivalent to the probability of B given AC. This is the probability of A given C. This is Bayes. We did that quite a while ago. We need that rule. This is the only rules we're going to need, and a little bit of counting that I taught you. And then we had this probability of A given information plus the probability that A is false. And there's various ways to write A is false. Must equal 1. And that's basically it. And if we have the probability that A1, AI is one of I states out of n, and we have no other information about them, that one of these I states must be true, we have 1 over n. These 3 rules of probability, which we've already proved, give us everything else. All the rules in probability are now going to come from this. And I see that I'm running out of time, so I don't have time to go through this example in any depth, and I don't want to rush it because if I do, I'll lose more people than I already have. So I think we're going to be able to solve this thing right here. We're going to ask about what if we draw a red ball, what if we draw a white ball, what if we draw 3 red balls or however many white balls, and what order, and all these kind of things. We can answer all those questions with just with formulas like this and this. If we have this and this under our belt, we've got almost all the probability can be built up discretely and finitely, which is to say that for any problem, n is less than infinity, and we could solve all problems in a discrete and finite way. And I'm going to emphasize this later on. And we could bring things to the limit. We can let n approach infinity to get approximations and so forth, which are very useful. But of course, in reality, there's no infinite number of anything. So for physical models, at least, we always know that this is going to be an approximation. And so there's absolutely no, we can let n be as large as we like, and we'll do some infinity counting as I promised us. N could be mind-bogglingly huge, still less than infinity, and so absolutely no bar to all kind of probability paradoxes which seem to crop up disappear when n is finite, and things are discrete like this. Okay, let me give you the homework. But just that little bit we've done, and I rushed through, the examples, the counting examples. We could build all the probability up, and later we take things to the limit, and then that brings in all sorts of nice shortcuts. It makes the math a lot easier. In fact, calculus is a lot easier than counting. You're going to have to trust me on that. Calculus is much easier than counting. When we start having levels in counting with all these indices to take care of and count and ensure we have, you'll be grateful when calculus enters the field because it's just very difficult. But however, it's very exact. That's the beauty of it. We'll see how important that is. Okay, so suppose I have 70 objects. 1, 2, 3, 4, 70. And I want to take a group of just 5 of them. So one group might be 1, 2, 3, 4, 5. Another one might be 1, 2, 3, 4, 6. And so forth. Or one might be, 70, 2, 3, 4, 6. Whatever you like. How many different groups can I get? How many different groups? Okay, you already have the tool for that. That's that permutation idea. And then this is going to turn into be like the library problem. I have a second group of objects that are labeled 1 through separately 25. I'm going to just choose one of them. I'm going to just choose one. Here I have to choose 5. Here I choose 1. How many different ways? So what's the ways? How many ways? Number of ways? Number of groups right there. So how many groups here? This is an easy one. This better be easy. How many groups here? Then the question is, if I first want to choose this and I'm going to choose this, how many total groups are there? I'm going to first choose 5 out of this, and then I'm going to choose 1 out of this. How many total groups? This becomes like the library problem again. How many total groups? I'll let you answer that. That's A of our homework. And B is this. I can either add 19 more balls plus 19. Oh, I gave the game away here. I'm going to add 18 numbers here. 18 numbers from 71 up to 99. Or I could say choose 6. Choose groups of 6. Which of these gives bigger total number of groups? Which is bigger. Now, if you haven't studied that counting stuff real well, you'll have to go back, look at the lecture. I will provide some links. There'll be some stuff in the notes. You'll be able to figure this out. Just to get your hand in and seeing how difficult this counting stuff can be. Next time we move on to Jane's and look at those two important lessons I taught us again. We're going to learn over and over and over. And I promise you, once we get to the end of this class, you're going to say, why can't people understand this? And they wouldn't make all these mistakes that they're making. On the site, for instance, I'm always looking at bad papers. And now we know why, because they're making these kinds of mistakes. That's it for this time. Thanks for listening. Oh, information is down below.